Now that we've got access to the derivative shortcuts for all of our trigonometric functions, I'd like to demonstrate a couple of them with the following problems. We're going to differentiate the following functions. We're going to start with f of x is equal to x squared times the secant of x. I notice in its current form it's expressed as a product of two functions, so we are going to proceed by making use of the product rule. So with that in mind, product rule states that in order to take this derivative, we are going to need the first function times the derivative of the second function plus the second function times the derivative of our first function. Now, simplifying all of these derivatives, we have x squared times derivative of the secant of x would be the secant of x times the tangent of x. Then we would have the secant of x times the derivative of x squared, that would be 2x. Now at this point the calculus of the problem is done. If you are interested in doing some additional algebra, there are some greatest common factors you could pull out. For example, they do have an x and a secant of x in common, and if I were to factor those out, your first term could become x times the tangent of x, and your second term could become 2. Now, while it is not 100% necessary to factor once we're done, later on in the course we're going to be doing additional algebra additional algebraic operations after we have taken a derivative, so it's a good habit to get into. For our second function, we have g of x is equal to the sine of x divided by x cubed. In its current form, we currently have a quotient, so we will proceed by making use of the quotient rule. For the quotient rule, this will be g prime of x is equal to low d high less high d low over the square of what's below. Doesn't finish the process for us, but it does get it into a slightly nicer form for these derivatives. That'll be x cubed times derivative of the sine of x, which is the cosine of x, minus sine of x times the derivative of x cubed, that'll be 3x squared, all over x cubed squared, that would be x raised to the 6th power. Now, as we did with the previous problem, at this point we can factor out a greatest common factor from the numerator in the form of an x squared. Now, I would consider it to be a little more necessary on this one because we're not done reducing the fraction. Once we pull out an x squared and we have an x to the 6th in the denominator, we can go ahead and reduce this down a bit. So x times the cosine of x minus 3 sine of x. When we cancel the x squared with the x to the 6th, we will be left with an x to the 4th power in the denominator. And finally, one more example. For this, we'll go to the back of the sheet. The function that we have is y equals the cotangent of x divided by the cosecant of x. Now, written in its current form, this would be considered a quotient, so let's proceed by making use of the quotient rule. So, same as what we saw on the last example, this will be low d high less high d low over the square of what's below. Quotient rule doesn't finish all of the derivatives for us, but it does give us some more basic forms for us to try to work with. So this will be cosecant of x times derivative of cotangent of x, which is negative cosecant squared of x, minus cotangent of x times the derivative of the cosecant of x, which is negative cosecant of x times cotangent of x. This is all over the cosecant squared of x. Now it looks like we're going to be able to do quite a bit with this. As far as a greatest common factor from the numerator is concerned, I would actually like to pull out a negative cosecant of x. So from the first term, if we take away the negative and the cosecant of x, we'll be left with the cosecant squared of x. In the second case, since we had two negatives and we're factoring one out, we'll be left with a negative. Take away the cosecant of x, we're left with cotangent of x times cotangent of x, which is cotangent squared of x. Denominator remains the same. Now with that in mind, you may not recognize it immediately, but anytime you see squares of trig functions, you should take a look around for a Pythagorean identity, and in this case there is one. This is equal to 1. Now, because we already factored out a cosecant of x, we could cancel out the remaining cosecant of x with one of them from the denominator and call this negative 1 over the cosecant of x. But if you'll kindly recall, the reciprocal of the cosecant function is the sine function. So after all is said and done, we have ourselves a negative sine of x. Now, a phrase that you are going to hear from me a lot this semester is that a little bit of algebra and trigonometry can save you a lot of calculus. I would like to reinvestigate the last couple of problems and point out that there are technically alternate ways to do these problems. When you are dividing by x cubed, that is the same as saying that you are multiplying by x to the negative 3 power. So if you wanted to proceed with the product rule, making use of the power and the sine rule, you certainly could. Now I just tried doing that in my head and I wound up getting the exact same thing as we did here. Now on the other side of the page, a little bit of algebra and trigonometry can save you a lot of calculus, because if you take a look at the cotangent of x divided by the cosecant of x, and apply some fundamental identities to that. The cotangent of x is the cosine of x divided by the sine of x, and the cosecant of x is 1 over the sine of x. If you cancel out the over sine of x's, you're left with just the cosine of x. And indeed, when we differentiated this function, we wound up with the negative sine of x. Probably would have been a little bit easier to do it that way than to go through all of this. So please let this be a lesson to you. Just because you observe something right away does not mean that you're not allowed to make alterations to it using algebraic and trigonometric rules that you know from your previous classes. Mastery of those rules is going to make this semester a lot easier for you.